So there's a theorem that says if k is the number of hypotheses in our hypothesis class, m is the number of examples, delta is fixed, then with probability at least 1 minus delta, we have this expression here. And here, what we are saying here is, first, here is a generalization error of the best hypothesis trained with our data set. This is going to be less, or at most is going to be equal to this expression here. Here we have two components. This first component will make reference to our bias, because it says here the minimum of the errors that can be generated, or the generalization error, with considering every possible hypothesis in our hypothesis class. And when we switch from some hypothesis class to some h prime in such a way that this h prime, let's say it's a larger set of hypotheses than h, this term, the first term, can only decrease. So if we, what we are saying, if we are going to consider more hypotheses, the only possibility that we can have is that in this new set of hypotheses, we can find a better model. And if this is a better model, then we will reduce of this error. Okay, so by doing that, we are decreasing our bias. We are decreasing the error when we increase the possible hypothesis that we are considering. However, if k increases, so now we are talking about this second component, then the second term will also increase. Okay, so, and k is the number of hypotheses. So if we increase this expression will increase, because we are now considering more hypotheses, and this expression is going to give you a larger number. So in the end, we will increase this upper bound. So if we increase the number of hypotheses, this error can only decrease, but this second term will increase. There is a corollary about this, which relates the number of training examples. And this is something we saw before, where there's a relationship between m and k, and this relationship is of a logarithm of k. So what we're saying here is the number of training examples that you need, if you increase the number k, is logarithm of k. So even if you increase the number of hypotheses that you want to analyze, the number of training examples that you need for training this hypothesis will increase logarithmically. So it is, of course, much better to have this relationship instead of something exponential or even quadratic or linear. This is less complex than even linear complexity. Okay, so now, given a hypothesis, class H, we are going to talk about dimension, or a concept called Papnik-Cherbonenkis dimension. It is written VC of H. And this dimension, this VC dimension, is the size of the largest set of points that is perfectly classified by this family of hypotheses. Okay. And in this case, we are considering that this class H has an infinite number of hypotheses. So consider, for example, a family of lines that we can use to classify points in 2 dimensions, dimension x1 and x2. So in this plane, we can have an infinite number of straight lines. So our hypothesis class is infinite. And consider 3 points. Okay, so in this first plot, we have 3 points, and all of these are from the same class. They are crosses. So if we want to perfectly classify these 3, we can draw, for example, our line here and say everything that is on top of this, above this line, is going to be a cross. And we have solved this problem, this instance of the problem. If the labels of these 3 points were like this, like 2 crosses here and 1 circle here, then the straight line could be drawn here. And by doing this, we can solve this perfectly. If the labels were like cross, cross, and circle, then the straight line should be like this. And so in these 4 plots, you see all the possible labels of the points, and you see that you can find a line to perfectly solve the problems. So in this case, this particular case, we say that the VC dimension of the model is 3, because that's the largest number of points that we can perfectly classify using straight lines. Okay, so if we had, for example, 4 points, then we can label the points in such a way that it would be impossible to perfectly classify, considering all the possible labels of the points. Remember the XOR problem, in which we have each point in a corner of a square, and points in opposite corners have the same label. So that example would be impossible to solve, to perfectly classify. So for this specific case of points in 2 dimensions, and being the hypothesis class straight lines, the maximum number of points that can be perfectly classified is 3, and that is the VC dimension for that class. So using this concept of VC dimension, if we call this simply D, the dimension of an infinite class H, then there's a result saying that the probability, with a probability at least 1 minus delta, we have that for all H in our class, we have this result. So again, we are seeing here the generalization error, the empirical error, and it says that the difference between these will be at most, or will be upper bounded by a complexity of this expression, in which we see here logarithms here, logarithm here again, and they are logarithms of m, in this case divided by the dimension, the VC dimension. So with probability at least 1 minus delta, we also have that the generalization error of the hypothesis, best hypothesis in our training set, will be bounded by the generalization error with the best hypothesis that we can ever found for this class H, big H, and this expression. So in other words, if a hypothesis class has finite dimension VC, then uniform convergence occurs as m becomes large. This allows us to give a bound, or to relate the generalization error and the error with the best hypothesis that we can find. So again, we are saying that the error, the difference between the expected error and the estimated error, is going to be bounded by the number of examples. So as we increase the number of examples, we are going to reduce the distance between the expected empirical error and the generalization error. And in this case, this is a result for infinite number of hypotheses given in a certain hypothesis class. So thank you. I hope this is useful and talk to you later. Bye.